right, perfect. Hello, everyone. Thank you very much for coming today. I'm going to talk about Anoma today. And really, Anoma is the first generalized intent-centric architecture. And the way to think about this is that intents are going to be the building blocks of the next wave of third-generation blockchains. And Anoma is the first of its kind. And it's important to understand here, sort of at a very high level, what intents are. Intents are the fundamental units that represent what users actually do on decentralized systems. Transactions are very poorly designed representation in this case, actually, because a transaction can only encompass something that is a fully valid state transition, right? When you think of sending, for example, a transfer on Bitcoin to another address, yes, that is a fully fledged state transition that is immediately executable on chain. However, most interactions don't actually look like this. Like if you want to be part of a multisig or you want to sell an NFT against some ETH, that's always a partial state transition, or what we call an intent. And really, Anoma is the first time that someone has proposed a generalized intent-centric architecture. And I can almost guarantee you that all major L1s going forward will be built around this idea of intents, just like all major L1s post-Ethereum were built around, or are built around, the idea of VMs and sequential execution. And with that, let's get started. So to start with, I'd like to go through a quick evolution of the protocol, sort of like how we got to today's state. And really, this starts with scriptable settlement, or generation 1. And this was all started with Bitcoin in 2008. And scriptable settlement platforms make for really good base layers for cryptocurrencies, something that like tries to be digital gold, like Bitcoin. But they're limited, but not completely impossible to build things on either. You can build things like colored coins, you can build things like Namecoin, and of course you also have the long tail of Bitcoin-like forks. And really in this category of chains, you have things like Zcash, Monero, Dash, Litecoin, and sort of the many evolutions of scriptable settlement platforms that came prior to Ethereum. And then in 2015, we got Ethereum, which really took this idea of Bitcoin, of scriptable settlement, of scriptable transactions, and try to make this programmable, right? So the major difference is that instead of having a limited scripting environment, now we had a full-fledged Turing-complete programming environment. And all of a sudden, things like colored coins turned into ERC20s, Namecoin turned into ENS, but we also got a host of other new things that sort of didn't exist beforehand, like DAOs, or new kinds of assets like NFTs. And this was actually very hard to predict in the early days of Ethereum, what kind of interesting things were going to be built on this very novel architecture. Because it fundamentally, I think the two big things it achieved is it made composability about an order of magnitude higher, because all of a sudden you had composability at the settlement layer where transaction actually happens. Whereas in the previous example of scriptable settlement, all these things had to be their own forks and you didn't really have a shared settlement layer. And at the same time, applications became an order of magnitude easier to build because you didn't have to fork the Bitcoin Core C++ code base. You could rather learn Solidity, which, albeit not perfect, is still sort of tremendously easier to learn than something like Bitcoin script, or forking Bitcoin. And sort of what is going to happen is that we're going to see the same orders of magnitude improvements in terms of both composability as well as ease of development in the next wave of intent-centric third-generation blockchains. I'd like to also quickly go through sort of what I would call programmable settlement plus plus, or second generation plus plus, which is what has happened since Ethereum. And this is really, we've made tremendous advances in things like Sybil resistance with regards to proof of stake, advances in scaling with things like near sharding, advances in privacy with zero knowledge proofs, which really came about post Ethereum launch, and also advances in consensus. And sort of, I think, but fundamentally, the important thing to remember is that most of these systems are sequentially executed VMs, where the thing that actually happens on chain is at its base a transaction and not an intent. And you sort of have to figure out how to do counterparty discovery and distributed solving out of the system off-band. And you can't build applications that reasons about these systems. And now I'd like to go into the third generation of protocols, really the intent-centric protocols. We're moving now from the VM world to the intent-centric world. And here, I think Anoma is the first of its kind here. It's the first generalized proposed architecture for a fully intent-centric design. And really the way it came about is we looked at how to design these systems from first principles based on the idea that most of the applications nowadays are already kind of structured around this idea of intents, but no one had given it a name. Like when you think of how OpenSea, for example, works, right? Like in OpenSea, no one directly transacts on chain. They send a partial state transition to the OpenSea Web 2 server. The OpenSea Web 2 server collects a bunch of these things on this AWS instance in San Francisco, and then once it has enough of them that match, it settles them somewhere. Something like Gitcoin is really the same example, and this is even true for things like rollups. All these systems are sort of trying to build around, or like trying to hop around the idea of intents by building centralized Web 2 infrastructure to make intents actually work in practice. Because really intents aren't, you have to rethink how the base layer architecture works in order to make them work efficiently and integrate them well into applications. So what is Anoma? Really, the TLDR, it's the first ever intent-centric architecture that introduces a new paradigm for building infrastructure layers. It is designed to enable applications that involve infinite users issuing infinite number of intents, each of arbitrary complexity. And so we'll go through what this actually means in practice. When you think of what currently happens in the transaction-centric world, users really express not what they want. They express some specific execution trace. They express how to get the thing. When someone signs an Ethereum transaction to execute a trade on Uniswap, they don't specify the trade. They specify, here's an opcode, here's an entry point, and here's a bunch of opcodes that are allowed to modify my state. So they specify the execution trace that a program can take that at the end may have modified their state in some certain way. And intents flip this on its head, where users directly sign what they want rather than how to get it. And this has tremendous benefits. First of all, it's much safer for the actual users because users know exactly what they agree to. They don't have to read every single opcode in their call stack. They can just read which state change they've authorized. And secondly, they don't have to specify how to get it. As in, they don't have to figure out the path through the system that their intent takes. They can rather say, well, I want to trade some Bitcoin against ETH, and I actually don't care if there's a Uniswap pool under the hood, or there's one counterparty, or there's 1,000 counterparties, because they've just authorized a specific state change and didn't specify the execution trace that that intent should take. Really, in a super simple statement, intents are binding programmatic commitments to preferences. And the important thing here is they're arbitrary. They're just code. As in, an intent is just a piece of state plus a piece of code. And this code may be arbitrary in scope. And you can think of this as it allows you to write very complex applications like, I only want to participate in this multisig transaction if the weather in Seoul is nice. If the weather in Seoul is bad, I want to sell my ETH. Right? Like you can do arbitrary complex things that if they are settleable in some fashion, the system figures out how to do this. And they're fundamentally necessary to enable decentralized counterparty discovery, because one of the big challenges with the transaction-centric worldview is that ordering matters. As in, if you sign over execution traces, it matters in which order we execute them, because we haven't defined the sort of resulting state changes, and rather, so now it matters whether user A or user B came first, because they may start modifying similar parts of the state. In intents, you can interleave them in arbitrary ways because users have already fully agreed to the specific state changes they're willing to take. And this leads to a declarative paradigm for dApps. Really what this means is that a user can issue an intent. For example, here wants to trade one NFT against one ETH. And again, arbitrary, this could involve any number of assets created in any number of systems. They run via Anoma as a protocol. And really, at the end, the user only has to verify whether it was possible to settle and whether it actually ended up being settled or not. They don't have to worry about what exact flow through a system it takes, because if I want to trade an NFT against some ETH, what actually may happen under the hood is that there's like a 15-party ring trade to enable because there's maybe no direct liquid market for my NFT against ETH, but there's like some path that I can take for ETH to Bitcoin, Bitcoin to something else back to my NFT, right? So in this sense, you don't have to worry about whether there are specific counterparties with which you interact. You rather go, is anyone on any path able to settle this? And this is, some of you may have figured this out, solving which two NFTs or which number of intents are compatible with each other, that's computationally very hard, and this is sort of where solvers come in that I'm going to talk about in a sec. But before that, the other big thing is that it enables really good privacy guarantees. In an architecture like Anoma, whether an application is private is not a developer choice. There are applications and then there are users, and it's fundamentally a user-level choice whether they want to interact with applications privately or not. And this is because of the sort of structure of the intent. Any of the fields in an intent can be private. They can be authorized in zero knowledge, or so in the future they can even be authorized using fully homomorphic encryption. And as a result, when a user interacts with a DEX, for example, currently they have to make a choice: do I go to the privacy-preserving DEX or do I go to the transparent DEX? In Anoma, this choice doesn't exist. Because there's a DEX, and users choose what kind of data they want to reveal in their intents. However, these intents are still composable with each other. So even, let's say one user wants to say, I want to trade, I don't care, I want to trade transparently because it's computationally more efficient to do on my edge device, to only do transparent authorizations via normal signatures. And another user that has exactly the counter intent or the matching intent, the inverse, wants to do so privately. These two intents are still matchable and solvable and are composable on chain. Yeah. Right, and then so the rest still happens in exactly the same fashion. Okay, so this is the entire overview of the Anoma architecture as a sort of spelled out diagram. And really here on the far left, we have users that can make a choice on whether they want to issue transparent intents, shielded intents, or private intents, and really they correspond to normal signatures that, as we currently know them. Shielded intents use zero knowledge proofs, and private intents use fully homomorphic encryption to even get better privacy guarantees on the specific state changes that you want to deal with. These intents are then submitted to intent gossip nodes. And intent gossip nodes form a sparse, non-consensus critical network that can actually span multiple blockchains, which is kind of a cool thing because it allows us to have intents be settled on other systems. This is not actually, Anoma is an architecture, and I'll come to deployment models towards the end, but you can also use Anoma to make applications on Ethereum more flexible this way. So you have intent gossip nodes, they gossip around these intents. Different intent gossip nodes can make different trade-offs with regards to which intents they actually care about. Some may only care about fungible tokens, some may only care about NFT intents, some may care about all of them. The nice thing is intent gossip nodes have a financial incentive. They can take a portion of the fee for the routing. So for example, if I as an intent gossip node, I receive an intent, but I can't immediately settle this and solve for this intent, I can attach, let's say, a 10% cut of the fee that that intent has, which is what I consider my fair share of the fee for the routing of that liquidity. And then some other node, once it actually ends up being settled, everyone that sort of attached a fee claim gets a portion of the fee. Of course, I can also say things like I take all of the fees, in which case this intent is most likely dead, because why would anyone else do the hard computational work of actually solving for this intent? Then you have the mempool, then you have solvers actually, first, who look at a number of intents and go, which ones are compatible? And solving is NP hard. This is really, really complicated, but structurally very similar to, so in the real world, currently we have tons of solvers. Things like MVV front running is just a special case of Anoma and of intents. Things like market making, same thing. Even things like running a rollup or running a ZK prover, this is all special cases of intents, where individual users want to come together to have some shared compute done to some state transition. And so solvers, in the simplest case, when you think sort of like some user has A for B, another has B for C, and the third has C for A solver would find these intents and go, well, these three things are compatible, put them into a transaction, encrypt them against the encrypted mempool, which uses Fairview for decentralized threshold cryptography. In the first block, you only order encrypted transactions, and then on the next block, the validator jointly decrypts those transactions and actually executes them. And then the execution and verification part is quite interesting. this is where Tiger comes in. I'll speak a little bit more about Tiger towards the end. Again, Tiger is the unified execution environment of Anoma. It is one large ZK circuit that uses Halo 2 as a proof system. Effectively, it allows you to treat transparent shell as well as private intents as uniform within the execution environment. So that as a developer, you never really have to think about whether my application handles transparent or shell intents. Tiger just handles this. Yeah, and in the end, users can just check whether their intent was correctly settled or not. Right, coming to the stack. Tiger, the unified execution environment of Anoma, handles all forms of state. You can think of this as this is also actually the cool part is why Anomas can also be a incredibly efficient ZK rollup, because all of Tiger is just one large circuit, and you can deploy these verifiers to other systems. This means that, and this is really important to us because Anoma is an architecture. It is not a specific blockchain. You can deploy Anoma into whatever security model you as a user care about. And different users have very different valid trade-offs here. Some users may care about global Anoma. Other users, like my parents, would probably care about like localized chains run by the local government. But the entire idea behind Anoma as an architecture is that we have a homogeneous architecture that is deployable in heterogeneous security models so that users can fundamentally make a choice on what is the best security model for them, while at the same time using Typhon that handles the intent, gossip, and mempool and consensus, so that I can just issue an intent, I want to trade some ETH against Bitcoin on X security model. But you have a unified intent gossip network that spans many different deployments of Anoma as a protocol. Yeah, and here Typhon is really cool. Typhon allows you to get multi-chain atomic settlement working, for example. If you're familiar kind of with modern BFT systems, Typhon is an extension to them in the sense that sort of in the normal case you have just standard BFT, but in the fancy case you get on-demand sharding with Typhon, that two chains can say, well, for 1 hour every month we want to be in a sharded synchronous environment. Then we have Vampire. I've spoken a lot about zero-knowledge circuits and privacy-preserving applications. This is all enabled by, well, not all of it is enabled, but in order to make developers sort of happier, we have Vampire, which is an intermediate representation for circuits. Think of this as LLVM. LLVM, but for circuits. It is really just a basic representation of circuits. For now, developers can write this directly. In the future, I would expect this mostly to be a compiler target, as in there are high-level languages that target Vampire, because one of the really big benefits is that Vampire is fully proof system agnostic. So currently, Vampire supports PlonkUp and Halo 2 as a backend, but there are also experimental backends in the work for Starks and for FHE. So really, as a developer, you can write one application, one circuit, and then later on, it's a compiler choice whether you want a Halo 2 proof system under the hood or you want a PlonkUp proof system under the hood. And this is really, really important because currently developers have to make very fundamental choices on their language side on what proof system the application should target forever. Right? This is also so that if in the future, which we're going to come across much better proof systems, not all applications need to be rewritten in the new languages. They can rather go, well, I've written this in Vampire, let's just build this. One person has to build a backend for the new proof system, and all of a sudden, all applications just work against the new proof system. This is kind of why LLVM for programming languages was so fascinating, because all of a sudden, you didn't have to worry about like, oh, my language only supports a specific chip architecture, like AMD or x86. Rather, I write something that targets LLVM, and then LLVM handles the hard part of translating this into a specific chip architecture. And then we also have Juvix, which is actually one of the first languages that targets Vampire. So Juvix at a high level is a high-level functional programming language created for creating dApps and programs that compile both to WASM as well as to Vampire and circuits as a result. You can use Juvix via Vampire to write circuits for really arbitrary systems. Wherever you want to, you can execute specific proof systems. You can use Juvix to write programs for that. And one of the very nice things about Juvix is that developers don't have to know anymore what like a field element is. One of the big problems is sort of that the abstraction for these circuit languages is still at the level of you have to understand how the cryptography works. With Juvix, it's starting to go away, where as a developer, you don't have to understand what a field element is. you can rather write a high-level program that then compiles down to a circuit afterwards. So what can you build with Anoma? And here, really, you can build a bunch of known dApps, but fully decentralized. So when you think of, let's say, the rollup space, you can build optimistic or ZK rollups, but fully decentralized. And currently, really, all these systems are massively decentralized because there's always a single Web 2 server somewhere in the stack, whether this is Optimism, Arbitrum, even something like Starknet, or even OpenSea. Structurally, they're all the same. There's always a Web 2 server running somewhere that does the decentralized counterparty discovery and distributed solving component, except that it's not decentralized and not distributed at the moment. You can also build DEXs because Anoma allows you to have intents which are not on-chain. So intents can be free. So you can actually build very scalable order book exchanges without having to have centralized components like the relayers in the 0x model. We already spoken about NFT marketplaces. The important thing to understand, this is like, even things like Gitcoin are, at the moment, somewhat centralized because the quadratic funding formula is actually being run in some Excel spreadsheet, and then sort of the results of that Excel spreadsheet output are being submitted on chain. This isn't fully decentralized yet, but if you wanted to build this with intents, you can actually just say individual funders or donors issue intents, and once you have enough intents together, anyone in the world can run the solver, and then this is executed on chain with a solution proposed by the solver. You can also build a bunch of novel things, though. For example, like runtime rollups. Intents are just partial state transitions. If I have an intent from A to B, and someone else in the audience has an intent from B to C, any solver in the world can create a partial solve from A to C, which means that sort of at the networking level, rollups just exist all the time, which is also really important for sort of computationally hard or complex solves, because maybe I only have the solution from A to C, but not C back to A. I can still charge a fee for doing the partial compute of the sort of collapsing of the state from A to C without having to worry about also having to do C to A, because I can rely on the fact that if this is possible, someone else can create C to A and then settle the entire thing where my solution is still useful. You can build DeFi dApps such as with like sealed bid auctions, privacy-preserving DAOs, and sort of new age game economic systems like Pro Money and collaborative finance. So this is an example of KryptoSeoul in a fully decentralized fashion. Because right now there's, again, a central coordinator that everyone interacts with, that the sort of users submit their trades to, and that solvers talk to in order to get the batch that enforces both the batching requirement as well as the optimality of the solution. In Anoma, users would submit these intents to the intent gossip layer. They would be encrypted for a application-defined interval. So I mentioned the encrypted mempool with Fervio. The nice thing is this primitive is also exposed to the application developer. So an application can define custom decryption thresholds. So for example, a KryptoSeoul application on Anoma can say things like, I want to have my batch length as 10 blocks. During those 10 blocks, users can submit encrypted traits to that batch. After 10 blocks, the validator set goes and decrypts all those transactions. And then solvers maybe get another 5 blocks to submit valid solutions. I think the really important thing to realize is that like when Ethereum came out in 2015, we really couldn't spell out all the applications it would enable. And I kind of think this is going to be the same with Anoma and the sort of third generation of applications, or third generation of blockchains here, because fundamentally this is just going to enable a bunch of new stuff that we are going to have a hard time thinking about. This is going to really enable decentralized applications at global scale and many different security models. Because just very quickly on the deployment models, you can deploy Anoma as an architecture as an L1. You can also deploy this as an L1.5 to sort of just decentralize a specific application, or you can deploy this as an L2 on a settlement layer like Ethereum or other systems. Really, like the security model should be a user choice. We don't have a one world government for a very good reason, which is having one global security model is kind of fucking terrifying. We should have many independent security models that can talk to each other, but can fail independently of each other. Yeah, so Anoma is founded by myself, Awa, and Chris, and built by one of the first core development teams at Helix. Thank you very much. If you want to connect with us, those are the QR codes. Thanks.